So I'm just checking something. Okay. So, if I had something like, this is just a general idea. If I were being asked to d dx y to the power x, okay, what would that look like? Okay, d dx y to the x. Now, just out of the blue, and thinking about y to the x, what is another way? I'm looking for another form. This is really important, I feel. This is why I've gone off on a bit of a tangent. This is quite important to this process. What's another way of writing y to the x? Okay. And another way of writing y to the x is to consider the use of e and ln. Okay. Now, in order to get e and ln involved, remember e and ln are undo. For all intents and purposes, it equals 1, favourite number. Okay? But if I think about this for a moment, if I were going to use e and ln, and I wanted it to be the same, I couldn't just write the ln of y, because that would be just y. That's not fair. I would need to put the x up there as well. Okay, so I haven't messed anything up in the equation. Do you agree with that? E and ln are undo. So now, e and ln, now using the log laws, I can put this x down here. So I can say that x ln y. So y to the x equals e to the x ln y. Okay, now that's helpful. Right, why is that helpful? Because it helps us to explain why the raising to the power results in another part. Sorry, every time I put my pen down, it messes with my mouse. I've just got to put it in the right place. So let's do d dx of this. Let's do d dx. So how would we do that? We would say let u equals x. This is quite important, so don't lose sight of that. And du dx would be equal to, for all intents and purposes, this is a constant. So we would be left with ln y. We would be d duing e to the u, and we would put those together. So we would end up with the ln of y, e to the x ln of y. And it only comes up when you're differentiating these guys. So what we end up with is a ln function multiplied by. Now, how does that differ for anything else that we want to do. So let's try it. Let's try it for this one. Let's say we've got y equals 2 to the x. Use our little method. Okay, what would that look like? That would be an equivalent form. Okay, but this time instead of using log ln, we use log base 2. Okay, so we'd have 2 to the power log base n. So 2 to the x log 2 y. No, log 2, sorry, that's got to be a number 2. And that's got to be base 2. So that's x up there is 2 to the power x. 2 undoes log 2, so that's a tick. Okay, so that works. So then you can go off and you can we can use e. It doesn't really matter if we use e, because e would be just as effective. So because we can do it this way, x ln 2, it would be just as effective. Okay, so we can let u equals x ln 2, which is a constant. So du dx is just ln 2, d to u, e to the u is just e to the u. So put them back together and we get dy dx equals e to the x ln 2, but there's a ln 2 out the front. Okay, so I'm not sure how much you've been drilled on doing that, but e and ln are very, very powerful allies when we need to get into differentiation of bits and pieces. So back at our practice questions, in a way the fact that it's a ln is irrelevant, because ln and powers are related. Okay, so if we do let you so that's our part, and the other part was the ln of u. So our final answer is going to be those two chained together. And when you put all those together, you get 1 over 6x. So there's a little bit of thinking that you've just got to be wary of when you're doing those, differentiating those, and it's not straightforward. Alright, sorry for the rigmarole there, but we just needed to pause a little bit and think about that. Now, having said that, just beware that the ddx of ln of x is straightforward, or any variation. Okay, however, the integral of ln of x is not. Okay, this requires integration by parts. So just we'll get to that. We'll get to that. All right. All right, differentiate the following function. Boy, goodness gracious me. Okay, So the first thing we can do is invoke log laws. So that's a T and a plus, and that's a T and a minus. So once you get it into that form, then it's just a chain rule. So for this one, okay, and so then it would be D to U now that's a double chain, is it? I think I had to do that because we'd be D to Uing the ln of U. So I think this is a double chain, so I've jumped the gun there. Alright, so for these guys, let U be the whole thing, then you get the ln of U, so that's your substitution. This though is a problem because now we need to let M equal to T plus 1 and U will be equal to M squared. So du dm will be one thing and dm dt. So it's a triple chain. We did go through this. So that's 2, that's 2m, and we put all the chains together, we'll get 4m, which is 2t plus 1, the ln of u, which is 2t plus 1 squared. And I'll let you finish that one off. Hang on. We're going to pause. I've done it again. Let's try this. I said use the log laws, but I didn't take it far enough. I don't think. So we've still got f of t there. Sorry guys. So f of t there. Now what do I do here? I've done it before, I did it on the previous page. I don't know why I didn't register that. So let's make life a bit easier and bring the power down the front. Because they're logs, we can do that. Now we no longer have these chain rules that go double chain. Okay, so just be careful with that. Alright, the logs allow us to pull these apart. Okay. Alright, so let's do it the U, let and that leaves D U3 ln U, which will be equal to 3 over U, which will be equal to 3 over 2t plus 1. Now we're going to put them together, so that side will be 6 over 2t plus 1. that's done. Alright, so we'll let m equal 2t minus 1, dm dt is equal to 2. That leaves d dm.
Sorry, how did you go from the 3 on 2t plus 1 to the 6 on 2t plus 1?
Because this is a chain. So 3 times 2.
Ah, yep, okay.
Sorry, I didn't put it up there. 3 times 2. So this one here is minus 4 over m, which is minus 4 over 2t minus 1. And then we're timesing them. So we end up with minus 8 over 2t minus 1. Alright, so they're together. So I'll just run out of room. I'll just do it like this. So that equals okay. Now the problem you've got there is that you want to simplify this. You've done the differential calculus, you've got your f of x, so you give yourself a big tick, but then you've got to make a decision or ask your teacher about whether or not you want these fixed up. So they are not the same, so this is an adding fractions problem. So you've got to go through and do a product. Okay, so I'm just going to bring it over here and move this up. And so we've got we've got to multiply through to get them into the same family. That's the basic idea, isn't it? So the product's going to be the product of these guys. But I'm leaving them as factors. You can understand that, right? They're the same thing. Now, how did this side become that? You multiplied by this, so what you do to the bottom, you do to the top. And it was 6 outside of 2t minus 1. And what you do to the bottom, you do to the top. So it'll be minus 8 outside of 2t plus 1. Okay, now you can write it as a family. 6 2t minus 1 minus 8 2t plus 1 over the same family. I honestly, I don't like this level of algebra in this subject. I think this is just a waste of your time, to be honest, and I'll be shot for saying that. So 12t minus 6 minus 8 16t minus 8 and what do we got there? 4t squared. These are the difference of two squares. Okay, so you can just write 1. Now I better explain that. So let's just fix this up. 12 minus 18, is it? 2 8s are 16.
16, yep.
16. So it's minus 4t. 6 and 8 is 14. Now, how did that happen? 4t minus 1. So that's your final, that's going to be your final answer. Now, a minus b, a plus b. So if you do your FOIL, you get a squared minus ab plus ab minus b squared. So that's 0. So you're left with a squared minus b squared. So anytime you get a pairing like that, you can go for it. So this is this pairing here. So that form matches that form. They're the same things, plus or minus. And whenever you get that, you'll recognise them as the difference of two squares. Okay, so that's a tricky one. Don't know why it's there. You learn that stuff as you go through your life. It's not necessary for you to have it assessed now, but that's just my opinion. You've done the equivalent at school of foundation maths, so for me that's a bit annoying. The fact that you got to this point here was enough for me. The fact that you got to there. Alright, let's go back to our practice questions. Alright, differentiate the function. Okay, so what can we do with this? Okay, so this is a very troublesome problem. Whenever you have something multiplied by a square root, okay, with something else in the square root, you have to get it in. How? How do you get it in? Okay, and you need to have it in a square root, because if it's a square root, then you can just do that. Okay, but how do we change this from square root? Well, we have to square it. So whatever else it is squared. Then you can put that in like that. Okay, so for this one here, in rewriting this, we would have to write the ln of the square root of x squared, which seems stupid. Okay, but that allows us to bring it in. The reason I'm leaving it out is because this occurs somewhere else. Now you have the 1 square root sign, but you have x squared bracketed with what the other multiplication was, because you're multiplying expressions. Okay, so we've got the ln of the square root of x4 minus 12x squared. Even funnier than that is that you've got a logarithm with a power to its argument. So guess what you're allowed to do with that? Send it down the front. So even before we've done any differentiation, we've managed to get it looking quite simple. Okay, now at this point, now that's a lot of work there. For me, foundation maths should have taught you that, or whatever maths you came out of high school with, you should have been supremely confident with those steps. But I find many students can't deal with that until it gets introduced to them the way we've done today. Okay, so hopefully you're feeling a bit more confident. Now, of course, you can go off and do your differentiation, okay, which is going to be what? So we're going to take the u, and we're going to say let u equal x4 minus 12x squared, and du dx will be equal to 4x3 minus 24x. Okay, then we will have had over here d du. I can write it as q of u equals, or g of u, sorry, g of u is equal to a half the ln of u, but I've been skipping that. Just this is why I taught you expressions. Find the differential of the ln of u, and you're going to get 1 over 2 times u, which is equal to 1 over 2 times all of that stuff. Okay, now they're a product, they're a big times, the chain. So g of x dash is going to be this one here, times this one here, and so you'll get what's common there? 4? Can we bring a 4 out? 4x3 minus 6x. Or what about a 2? Because there's a 2 here, isn't there? Let's make it 2. Let's just get rid of that 2 on the denominator. That's why I'm doing this. So I'll take 2 out of this numerator. So the numerator will be 2 times 2x3 minus 2 12s are 24x. And then we had the 2 underneath, so they'll now cancel. And you're left with 2x squared, should be. Oh no, that's right. Maybe we could take an x out of these. Sometimes you don't see things until you take the brackets away. But I'm thinking we could take an x out of both terms. We can't take an x squared out, but we could certainly take an x out. Top and bottom. So they'll cancel. And so you're just left with that. Okay. So a little bit annoying, but like I'm saying, I don't like the level of algebra that's been put in, because you shouldn't be being assessed on algebra. You should be being assessed on exact values, trig and inverses and all of that stuff. And the level of complexity of algebra, you can follow that through at a later stage. So just lower the stakes a little bit in my way of thinking, but I'll probably get shot for saying that. Find the equation of the tangential line to the curve. Really? This is like year 10 stuff. Really? No, I don't want to do this. This is really... Alright, so let u equal x. You shouldn't be doing this in Maths 1. I'm such a whinger. And y was equal to the ln of u. So dy du, there's the equals 1 over u, there's your chain. So y dash will be equal to 2x over x squared minus 8. Okay, now x is 3 and y is 3, so it wants to find the equation of the tangent. So we have to go to that point. Remember that this is m. Okay, so that's very helpful. So using function notation, if I go to the 3 value, okay, I'll get 2, I always use brackets, 8. So we've got 2 3s are 6, and 9 minus 8 is 1, so the gradient is 6. Okay, now that's the question about the tangent, so I'm going to call it MT. So the other thing we've got is we've got our general equation, mx plus b, and at the moment we have all the information except b. M is 6, and we've got solutions 3, so I'm going to use those solutions. 6, 3, so they're the points 3, 0, plus b. Okay, so therefore b is equal to negative 18. So yt will be equal to 6x minus 18. Okay, that's year 10 stuff. I get kids in year 9 to do that. Alright, so that's not to make you feel bad, it's just to say, alright, find the equation of the tangential line. Okay, so this is going to be an awkward product rule, is it? Okay, so whenever you have a product, you can rewrite it as the ln of A plus the ln of B. So we get y equals, there's your product. Okay, so that's not too bad. What do you notice? There it is. Undo. So we get the ln of x plus x to the 7. So that was a cheeky one. Nice use of the thingy, but now we can do the derivative. So the derivative is 1 over x plus 7x 6. And we've got the points again. So we're going to do function notation, because this is m. So it's going to be 1 over 1 plus 7, 1, which gives us 8. Okay, we go through and do it again. We've got solutions. So therefore b is equal to -8.
It should be -7.
The gradient's correct. The points are 1, 1. So 8 times 1 is 1. So b would be -8.
So the last equation is 1 equal to 8 plus b, so b is -7 instead of -8.
Because it'll be 1 minus 8.
Ah, my bad. Yeah, okay. See what happens when you go too quickly? You make mistakes. Okay, you happy with that? That's the solution we want. Thanks for picking that up. Alright, so how are we going? Alright, logarithmic differentiation to find the derivative. So in this particular case, what they want you to do is to take the logs and muck around with the log laws. Okay, which is a little bit different to what I was doing before. So using log differentiation, so we're going to do, it's a product. So it's AB as a product. If we introduce logs, okay, we can split them up. So we can introduce the logs there, and we can get, but what you do to one side, you've got to do to the other. So we've got to do that. So we've broken the product and expressed it as a sum, but please remember to do the left-hand side. Okay? The other thing we can do is take the 5s down. And the 6. So far so good. I think you're ready to differentiate. Now what's the problem here? We're going to differentiate with respect to x, because it's y in terms of x. So what do we need to introduce here? We need to implicit. Okay? So we're going to ddx the whole thing, which means we're going to ddx each term. Okay. Alright, so that doesn't make any sense. So we have to invoke the chain rule. What fits? y fits. This one makes sense, but it's a chain. So let u equal 2x plus 1, 2. So we're going to end up multiplying by 2. I'm taking a bit of a shortcut. So it's going to be 10 ln, call out if you don't know what I just did. Hang on, it's going to be 1 over u. Might be better if I did it properly. So let u equal 2x plus 1 du dx equals 2 d du 5 ln of u is equal to 5 over u, which is 5 over 2x plus 1. Now we're going to times those together. So we end up with, now the d dy of ln of y is 1 over y. And 10 over 2x plus 1. And the other term, m equal now what's that going to be, a plus or a minus? I think we're still sticking with the plus, aren't we? 6 fours are 24 x cubed. Okay, and we didn't have to do any implicit there, so all we've got to do is put the y across, which is multiplying both sides, and y itself was this thing. In addition to the bracket, now clearly those denominators are not the same, and so there's a mile of algebra to get through. Okay, so expand and simplify. I'll leave you to do that because I don't think there's anything terribly exciting in there. Okay, so I'll let you do that. I think you get this sheet at some point anyway, don't you? Alright, if that's alright with you. Now, logarithmic differentiation. Again, take the log of both sides. That allows us to put the 4x down. We've got to do implicit. And you do it all again. Now if you get practiced at it, we can clearly see that's a product. We can clearly see this is going to be 1 on y with the dy dx left over. So you never use short form, you always use Leibniz notation when you implicit. Okay, and this will be u dv plus b du, but you've got to do that bit. Okay, and then you'll have y times. So 4x u dash is equal to 4, v dash is equal to 1 on x. So this becomes 4x on x, which is 3x. This becomes the ln of x, 4 times the ln of x. And we're going to multiply that by y in the same step. Now you can use your stupid little shortcuts if you want, and I'm sorry to say that, but they are. It's too dangerous. That's why I don't like shortcuts. Because when you get to this level of maths, too dangerous. Use Leibniz. And what's y? X 4x. So I'll leave you to do the last bit. For your expansion and simplification. Where did I get the 3 from? U is 4x. Oh, 4x over x. Huh. Should have been 4 plus 4 ln of x. You gotta watch him. Alright. Gee, we've done a lot today. How are we going for time? We alright? Yeah, we're okay. Alright, so the ln of x squared plus y squared. What are we doing with this? Just implicit straight off. So d dx so taking a shortcut, a bit naughty. So this one here, we have to be a little bit careful. Now when we do du dx, we actually mean d dx. So we're going to get du dx, and we're going to get 2x, but we're going to get 2y dy dx. The other part is the ln of u, which is 1 over u. So this product together will get 2x plus 2y dy dx and x squared plus y squared. So we can put, for the moment, let's put the x squared y squared up here. So we've got to get some parts on their own. We've got to solve for dy dx. We've got to get those terms on the same side. So we're going to have Yeah, I just want to do a bit of work on this one. Let me do a bit of work on this one. If that's okay. To there. So the only way to expand the terms I'm just wondering about this left hand side. If I do it this way, I think I've got it out there. Yeah. Alright, I think that's it. Alright, there's quite a bit there, isn't there? So the hard bit's implicitly differentiating up here, making sure you remember to do that. Then when you come to put them back together, it's to bring that up, because that's part of a times, which is like over. You can put them in brackets if you want. And then to put that back up into your equation. Okay. So you can recognise left and right parts. Alright, sorry about that, that's quite involved. Alright, back to our questions, if there's no more questions. 1 on y. So did I answer that for you, Jean? Jean, it's the y went up. I multiplied it both sides. So I took this and multiplied it both sides, and it ended up in both those terms. 2xy, and because otherwise it was just 2x. I missed a step there, man, that's all. I did it. I should have been a bit better here. I should have times by y. And so that 2x got a y, and that 2y squared it became a y. Does that answer that question? Sorry. Okay. Express the question in exponential form. Okay, so this is that recognition that we did. I did this. I touched on this very quickly. Okay. So if you raise everything to the power 5, this here is undo. Okay, so you get 5 equals 5 to the 1. Raise everything to the power 5. Anything raised to the power 0 is 1. This is undo, so 1 equals 1. Okay, 5 to the power 0 equals 1. So they're not that bad. Alright, express the exponential ln of 2, so raise everything to the e. That's undo, so therefore e to the x is equal to 2. I've just swapped them around. Same thing here, raise everything to the power e. So yeah, they're the ones that get you. Alright, next one. The position of the particle. So this is just like curve sketching of a particle's given below. So position. So velocity. To get a velocity, we'll need to differentiate. Okay. So s dash of t, we can use our little shortcuts because it's a polynomial. Velocity, so we're going to make that 3. Now to make life a bit easier, you can divide through by 3. Okay, and two numbers that add up and multiply, 6 and 5. So we've got a plus t, so we want a plus 6 and a minus 5. So therefore t is equal to minus 6 and 5. Because it's positive, it takes 5 seconds. Okay, find the time when s dash is 3. So we just did that, 5 seconds. Divide 3 by 3, I've skipped all that. Alright, find a formula for the inverse of the function y equals the ln of x. Okay, so this is where you want to take ease. Take ease for everything. That's undo. So e to the y is equal to x plus 4. So therefore x is equal to e to the y minus 4. So then you can do your inverse thing. Because you're just swapping, you're swapping at this point. So rearrange and swap. Alright, was there anything else you had? I think that's it.
Yeah, I think that well and truly covers about everything.
Alright, so there's a lot of, I think the main gist of these, the curve sketching stuff, it's these e's and lns. This section has e's and lns, and it also has your differential what they're calling logarithmic differentiation. So there's quite a bit there, implicit, and then this has got your implicit, and it's got your inverse functions as well. So exact values, trig, and all that stuff. Alright, so how did you go with your tutorials?
Yeah, good. It's yeah, all the tests have gone very well for me so far. So yeah.
Alright, and tutorial 5's out as well. Now, was there anything we needed to do on integration before we went today? I'd like to just touch on a couple of things if you've still got enough head space. If you haven't got the head space, I understand.
I probably haven't got a lot left, but you can run through it for sure.
Alright, so I'll just do a map, okay? I'll just do a map, and then that way you can look at it later, okay? It's literally a list. Okay, so the first method of integration would be up and under. So if we have I've been doing other types. Now the difference between the two is that one of them gives you an expression and one of them gives you a number, which really should be considered an area. So an example of an upper and under actually I'm just going to move that. No, I don't want to do that. Okay, so that's that one. The next one is the quotient. So the quotient has the form of the derivative over the function. Okay. Actually, that should have been there. And you can use technology to check those. Then we've got the big one. We might leave that till next week. And then we've got trig sub. Then you have integration by parts. And partial fractions. And you need all of those to do the next parts. Alright, so that's a map, and that pretty much rounds out your integration. Okay, but the most important thing, like I emphasised the chain rule with you, is this guy. Okay, the chain rule is to differentiation, or U substitution is to integration, what chain rule is to differentiation. Okay, so I will walk you through U substitution next week as well. And that's it. That's pretty much, let's wind it up there. Okay. Alright, thanks guys. I will see you next week. Okay.
Thanks, Jason.
Alright.
Yeah. Thank you, Jason.
No worries. See you then. Bye now.